Okay, let me continue with what I started the last time. And if you recall, the last time I was telling you a fair amount about the basics of control, and then also a little bit about adaptive control, and a little bit about learning control in the last few minutes before I ran out of time. So I may run out of time again, but today we have a lot of time since the barbecue can be late. Who cares? Is that okay? No, maybe not. Okay, so fine, super fast. So where did we stop? We were watching videos, so let's do videos again. Some fun about robots.
This is the Exos 2, the closest thing we have at this moment to the Iron Man suit.
So it has nothing to do with robot learning, but it's kind of fun. Well, fun, this is the cool thing about robotics. You always have videos. It's kind of, if you get bored, just watch some videos. So this, nevertheless, it's kind of a cool robot. So it's essentially an exoskeleton robot, and it's otherwise a totally normal robot, except that it basically feels what the human wants to do and just adds a lot of power and strength to the human, which is scary like hell. The thing in the Roman Empire, they used to rip people into 4 pieces with 4 horses. That machine can do it for you. It's very easy. So, fine. Another way of robotics basically making progress, and maybe it becomes an Iron Man at some point. We'll find out. Okay, now we got to be much drier again. Learning control. Let me go back to where I started and continue from there. Model-based control. So in the end, again, there's a lot of engineering in these systems, and we would like to automate them all. We would like to make them autonomous, add controllers which do the right thing. And in the end, actually, who cares about an exoskeleton suit? Wouldn't it be nice to take the human out and let the thing go by itself? I'll show you something at the end of the talk which goes towards that. So you also already saw that. I just want to remind you, we went through adaptive control, and what we actually did in adaptive control, we created a little function f of x and kind of approximated. It had just one parameter. It was super simple, but I could show you in this extremely simple example how people in control would actually create a learning controller, an adaptive controller, which basically puts stability theory right into the system as well. So stability theory and learning were put together, and what we got was a stable, guaranteed stable learning system, which is normally very hard to achieve in general. So in control system, again, there's lots of function we have to learn, and that's why I'm going to go over to function approximation in a second. Coordinate transformations, well, this is more classification. Control policies, then value functions, you will see what that is today, internal models, and again, lots of function approximations. So let's go a little bit into function approximation in general, not worry about the stability of a system anymore, but look at, so how can we actually learn these functions if we don't have them analytically? And many of these functions cannot be obtained analytically or not good enough to give good control. Again, what is very important, okay? Mean squared error criteria, or even normalized mean squared error criteria, they mean nothing in a control system. All what matters is whether the behavior works, is stable, and does what you want. Mean square, or normalized mean squared error of 0.9, what does that mean? It makes you maybe happy if you're a machine learning person. It may not make me happy at all, since that may be actually, I'm missing the target which I want to reach by 4 centimeters. That means I don't ever get my coffee, which is terrible. So it's a completely different game. And it's very important to keep this in mind. And there's a lot of people who do take actually robotics machine learning data sets and evaluate them in a standard machine learning way, which again doesn't tell me anything about the quality of how I can control with that. In reality, if you really want to evaluate, you have to put it in a closed loop controller. We have these things like PD or PID controllers on top, which do error rejections, which do compensation for a couple of things. And then you have to show me that it actually works in a practical behavior. All right, what's special about robotics and learning in robotics? So here's a couple of things which are worthwhile thinking about. Ideally, our robot system would like to learn incrementally. It's not that I can give you a bag of data and you learn from that. A robot like this is a humanoid robot that we have in the US, is a, what is this? It's a 49 or 50 dimensional system essentially. That means it has 50 position states. Then the state space of a second order system becomes this 100 dimensional, since I have to take positions and velocities. And some of the functions I have to learn become 150 dimensional in their input. Now these are spaces, there's just no way in the universe that you get a representative data set for what you want to do. You have to most of the time create the data yourself incrementally while you're running the system. Now the good thing is you can get large amounts of data, which is really great. The bad thing is you can get large amounts of crap data. That's not so good. So what's crap data? Here's the simplest case of really bad data. Standing still. I give you now at 1,000 hertz the same data point again and again and again. You're laughing, it's kind of funny, but yet it ruins a whole bunch of learning algorithms if you bombard them with the same or with a very tiny little bit of variation of the data point. So it's annoying. We want to learn continuously. Whenever you have to stop a learning algorithm, something is inherently wrong with you. They should be able to learn forever. That would be true and beautiful things to be, and that is essentially what these machines should be doing. You have no idea how complex the functions are which you have to learn. So Zubin talked about non-parametric learning today, at least from the few glances I got from the stream occasionally. And this is essentially what this is about. We don't know the number of parameters we need in order to basically represent the functions we care about. So essentially, we need pretty much potentially as many parameters as data points. At least we need a lot, and we don't know when it ends. What other things do we have? We would like to do fast learning. And there's actually two different kinds. There's data efficient learning and computationally efficient learning. So data efficient means I give a data point in, how long does it take in order to crunch with my learning system on it, in order to incorporate it and update everything I want to do. Computationally efficient, no, sorry, wrong way around. Data efficient is how can I squeeze the most information out of a data point. Computationally efficient is how can I do this in the fastest way. And now simple gradient descent algorithms, and I think you saw that in Steve's lecture today, can be very slow. So that is not necessarily data efficient. You don't get the most out of a data point, but it's computationally efficient and it's easy to compute. But if you take a higher order learning method, then you get actually much more data efficiency, but you have to also do more work in order to get it out. We care about real time, and real time, it's a complicated question what real time actually means. Our robots usually update about 500 to 1,000 hertz. So that's 2 milliseconds, what you can compute. Doesn't mean that that's actually the time in which we have to actually query a learning system to get information out of it. it doesn't necessarily mean we have to update the system at the same speed. That can be kind of a separate low priority thread which basically just updates the system at 10, 20 hertz, which would be totally acceptable. And last but not least, we're interested in robust learning. That means in my world, one thing is we would like to avoid interference. Interference, I'm not sure if they have talked about this, is the idea is, it happened particularly in old style neural networks. I train you on a data set, and now I give you another data set which has a different distribution than what you had before, and you will unlearn what you learned before because all the parameters will shift over and do something different. And that is essentially what people call interference at some point, and you would like to avoid that. There's an interesting trade-off between interference and generalization. Since if you want to generalize, you have to extrapolate or interpolate or do things like that. But when you do that, you can also create actually interference and unlearn something else. So this is an interesting back and forth. And in a perfectly ideal system, actually you would love to learn from hundreds, thousands, or maybe 10,000s or 100,000s of input data. So one pretty device in the back of your brain, your cerebellum, has on the order of about 100,000 inputs for every neuron. I have no idea what these neurons are coding, what these inputs are coding. There are all kinds of mixed signals, but somehow the system figured out how to very effectively use this information, pull out what is important, so most likely some kind of sparsification, and then use it for the purpose necessary. That's what we would like to accomplish, and we are far away from that so far. Okay, so let me start with something super simple, and most likely you have seen that before, and it's absolutely boring, but it's still pretty. Linear regression. Since it's something which works and is fast, and it's actually computational and data efficient. So just reminding you, here's an x-axis, a y-axis. I try to learn a function y of x. And that may be something similar as what we had in this little adaptive control problem, except this here was just one-dimensional. Now I can make this two-dimensional with an, well, it's still one-dimensional, but with an offset term now. I can make it multi-dimensional, it becomes a tangent plane. So what's interesting about linear regression? Okay, fine. I have to find a line which kind of fits these data points with minimal error. And you can imagine that somehow by attaching a spring to every data point onto the line and basically waiting how the system finds its equilibrium. It's a nice little analogy. There's a couple of things which you may not immediately see. And one of them is that my springs are straight, okay? It's not that I allow them to bend like this. They have to stay straight. Why is that the case? Because my assumption will be that noise is only in the y component. It's an additive noise to the function. It is not noise in the input. Don't forget that input noise changes the picture. And my linear regression model would not be optimal for input noise at all. Now in robotics, we have noise in every sensory data. There's nothing which is non-noisy. And some sensors may be extremely noisy. So these things can actually bother you. And I'm not going to address it since there are special models which can address it, but just think about it. It's important. Another thing is important. All the springs have the same spring constant, that is same springs. It means a data point which is far away pushes a lot, or pulls a lot on the line. Points which are close by pull little. If I had a data point down here, it would stretch the spring like hell and pull the entire line down. This is a typical example why linear regression is actually vulnerable to outliers. One bad data point, somehow one sensor spooking and doing something bad, and my entire line will tilt down and you get really bad results. Something to keep in mind. All right. Now, I assume you all know linear regression, roughly. Total, very fast reminder. So you can easily pack this on one slide. So there's now vector matrix notation in the end. So we just have a one-dimensional output, which is basically created by a weight vector transpose times some input vector and an offset term and a noise term. The noise has to be mean zero. If you derive it through maximum likelihood, you usually make it a Gaussian distribution. If you just derive it in this standard algebraic way, actually you just need to make it mean zero. So we basically can absorb that offset here by creating a new input vector, which basically includes the offset. The weight vector becomes slightly different. And that's kind of the setup. Then you have a least squares cost function simply written in vector notation. This is a vector of target points. This is what I would like to fit, what I want to come up with. Y is what my linear regression outputs. the matrix X basically has all the data points X as transpose in the rows. And then all what you got to do is minimize the cost function J with respect to the parameters W. And that looks like this. It's nothing particularly exciting. It's not pretty. I'm not going to go through that. What comes out of this is that standard linear regression equation. Very simple to basically write down, very simple to derive, and super simple to code. It takes you a couple of lines of code at most, if not one. All right. So it's a very useful model, but it's linear. It's kind of boring. Small remark, there is also this special incremental version of it, which people may remember or not, and that is kind of recursively squares. It's based on this, what is called the matrix inversion theorem. In case you have never seen it, it's lovely. It helps you in tons of different derivations. It comes in vector notation as well, in all kinds of versions. I mean, in matrix notation and partitioned matrix notation. But if you apply this and just write the least squares update equations incrementally, you basically end up with something like this. There is basically the inverted covariance matrix, which gets updated incrementally in this form. You basically now add just one data point new to the system. And then the weight vector gets updated like this. This is actually now for multidimensional output written, but doesn't matter. You can make it on little w, is the same. And then people often actually add something which is called a forgetting rate, which is in here. So the forgetting rate, if it's set to 1, then it's boring, then it's just 1 over 1 and everything disappears. If it's less than 1, between 0 and 1, usually 0.999 or something like that, you slowly forget what is in this inverted covariance matrix. And that was something you do if you have non-stationary problems to deal with. The beauty about recursively squares is if you don't do forgetting, after incorporating n data points, you have literally exactly the same result as you have with least squares. So this is an accurate method. This is not an approximation. So this is, again, something which is very useful if you try to create incremental algorithms, and I'll show you in a second why I want that. All right, now, Zubin. He created this diagram when I was drinking coffee and watching his stream from my office. So I thought I'd create this diagram too and make it even more colorful. So fine. It was a very useful diagram since I found myself back up here in the linear regression box, which I like. Ignore all that classification stuff. I don't care about that. And then he was basically talking about you could go downwards and basically make things nonlinear and it would come to a kernel regression, or you could go forward and it becomes Bayesian and then becomes Bayesian linear regression, or you could go down and then becomes Gaussian process regression, which is actually a very nice diagram. And I'm going to actually follow this diagram, except he forgot my box. Very annoying. There is another way to nonlinear Bayesian regression, and that is Bayesian kernel regression. And I'll show you this for a second as an alternative to other methods, just because it will remind you of a couple of machine learning techniques which are originally based on nearest neighbor methods and kernel regression, but which can be put in the graphical model context, in the Bayesian context, and approximated with variational methods, very similar as what you've already seen in various talks before. And it's actually, so Philip Henning and a student of mine have been starting to work on the connection between Gaussian process regression and Bayesian kernel regression. Actually, there is a way how to go from the one to the other model, except we haven't fully figured it out yet. So let's go and make linear regression nonlinear. And it's actually very simple. There's a technique which is called locally weighted regression. It's essentially based on kernel regression. Do you guys know what kernel regression is? Yes? Everybody? Hardly anybody? Cool. All this time goes away from your barbecue, you know? Fine. The idea of kernel regression was essentially you have somewhere a data space. Let's make it x1, x2. You have data points hopping around here. You want to basically fit some y. And you basically take a point of interest here. And then you look at the nearest neighbors. You can do k nearest neighbors, or you just create a kernel, some Gaussian, for instance, and look which data points fall inside. And then you take the weighted average. The weight comes from the activation of the Gaussian. So this is called a locally constant model, and that's kernel regression. The idea of weighted, locally weighted regression was just an extension from the 70s from a few statisticians where they started, okay, why do we use a locally constant model? Why don't we use a linear model? Or actually a higher order polynomial is fine too. Turns out that essentially first order, second order polynomials are the most efficient to work with. Higher order doesn't really buy you too much except for numerical problems. So this is the idea. So here's some arbitrary nonlinear function. Here's my little kernel, which is most of the time a Gaussian kernel. It's not the most, but you can actually choose these kernels in various ways. It turns out the most efficient kernel looks like this, like a pyramid. It's called the Epanetchnikov kernel, very strange name. Efficient means that it approximates the true slope the fastest with the fewest number of data points, it's statistical efficiency. But the Gaussian is much easier to work with, and this thing is totally discontinuous everywhere. It's a pain. Don't want to use it. So fine, we use this little Gaussian here. Then all we want to try to do is we create basically a tangent plane to the data which we have, or to the curve which we have. And we basically say it's only valid in a certain area, which is somehow delineated by this Gaussian function. And the way you do it is exactly the same way as I showed you now in linear regression. In recursive least squares, you just add that weight in your cost function. That means you simply say that data points which are far out in the Gaussian tail basically have a weight of 0, which essentially is they get clipped. And the simplest way of thinking about these kind of locally weighted models is actually if you use a super special kernel, which is just a box. It's 1 everywhere unless if you're inside and 0 when you're outside. And then you basically just means you're clipping the data set and focus on a certain area. This is just a smooth version of it. And linear regression now looks exactly the same way as weighted regression. And it's just one way of basically creating nonlinear regression. And again, you will see Gaussian processes. You will most likely see a support vector regression. You may see some mixture models. I'm not sure if anybody's going to talk about this in detail. These are all other ways of doing nonlinear regression. What's appealing about this method is that I can compute with it extremely fast. It is not as powerful as Gaussian process regression in smoothing with relatively few data points really nicely over your data. But we can create very fast algorithms. So let me show you what's the essence of these approaches then is. In essence, you have this big whatever nonlinear function. And what you're going to do is basically you start fitting these local models wherever you want. You could fit them at a big distance or at a smaller distance like shown here. The interesting thing is going to be is you fit them only by looking at the nearest neighbor in your kernel. You don't have to look at all the data points. And you fit these local models purely based on these local data points. It is not that one model left of you will influence what you're doing in your local model. That kind of avoids that you have to get interference. And essentially what you have to do is you just have to cover the input space with local models such that there's no gaps. And that's a very simple coverage argument. You basically say, okay, if I'm outside of a current Gaussian with less than 0.1, for instance, I create a new local model. So, okay. Let me show you how this works in a very simple algorithm. Again, we're basically now starting to create one local linear model. And now it's a tangent plane, standard equation as before. And we have a weighting kernel, which we make a Gaussian kernel. Just for algorithmic purposes, I'll decompose the Gaussian inverse covariance matrix with a Kolesko decomposition into MT and MM, which is what I need in order to gradient descent on that. I cannot do gradient descent on this matrix without losing its positive definiteness, essentially, otherwise. So this is just an algorithmic component. And when we try to make a prediction, we have lots of these local models, and all what we take is we take the weighted average of all their predictions, and that's it. That's our final prediction. How do you fit these things? Now, I already showed you that. That's why I actually showed it to you. The linear model I can fit with recursive least squares. It's now just weighted recursive least squares. The only thing which has changed is that here's the little w and here's the little w. The rest is exactly the same as you saw before. Very fast. It's a Newton method. So this really fits hell fast. What is more annoying is actually how to basically update the size and shape of the kernel. And that basically works with a gradient descent argument. And in there, well, this is the cost function we studied. And I think Steve so nicely said, he assumes you already figured out your cost function and your regularization term, and then he'll optimize it for you. And it's kind of the same thing. We had to figure out what is the right cost function to do it, and then figure out a way how to optimize it. There's one thing in here which is cute, just for a moment. Okay, just see that my timing doesn't run out. Have you talked about leave-one-out cross-validation? No. Huh. Impossible. So beautiful. Okay, leave-one-out cross-validation is one of the simplest way of regularizing your function fitting, so you have relatively good generalization. So the idea is you have some x, y, and you have some data points. And again, I'd want to fit a line through that, but I don't want to basically overfit what I'm having. And one way of doing that is, for instance, in order to create the prediction for this data point, I actually exclude it for a moment from the data set, compute the regression line, and then make a prediction for this input and see where it ends up. So this is a more stringent way of evaluating an error criterion. So fine, people do this in all kinds of algorithms all the time. Whenever you have to fit a parameter, you usually do it with leave-one-out cross-validation and basically can optimize something which is relatively safe to not overfit. It's not totally safe, but it's okay. The beauty is something, in linear models, there is actually a trick. Normal leave-one-out cross-validation, the way I showed you, would mean I have to go through the entire data set, exclude every data point, fit the line, compute the prediction, then note what was the error, then put it back inside, take the next one out, do the same thing again. So if I have n data points, I have to do n regressions. There turns out to be a little trick in linear regression. There is a closed form for the leave-one-out cross-validation error, which is just fun to know, since it can come very handy. And this is basically just using the yi minus the predictive yi, and then correcting it by 1 minus xi transpose the inverse covariance matrix of the regression xi. This computes leave-one-out cross-validation without that you ever have to leave one out the data point. It's very cool. It's kind of bizarre. You can basically, again, you can use the matrix inversion theorem, crunch to that, and you will figure it out. And that is actually what we had to put in here to make it robust. Why? It's a very simple thing. Local models have one really annoying problem. So if I wanted to fit, again, well, I could use that graph again, but here's another one. Okay, I wanted to fit the basically line. This is now a nonlinear function of some kind. I want to fit now at this data point with my little kernel down here. So what's the best width for this kernel to use? How wide? Small, big? Well, there's a really brilliant kernel. It's a little delta kernel. Since this one will fit this data point just perfectly well. It's fabulous. It's just it's total garbage because all what you get is delta function, no generalization. So you need to avoid this effect. In leave-one-out cross-validation, it does exactly that for me. It avoids that my kernels would shrink down and just focus on this one data point. So that's why we need it in there. And, well, yeah, fine. We did then basically gradient descent in this error criterion, and it's just a annoying derivation. Yes, please.
So I see that a bunch of local models will interpolate between points in the dataset very well, but what about extrapolating out?
Extrapolating out is the worst thing you should ever do in your life. It's a very simple answer. Why? Well, it depends what you want to do. You know, again, if you analyze a bag of words and want to extrapolate whether this web page came from what knows some miserable terrorist kind of person, who cares? Unless you start a war, that's bad. Our robots fall over. You know, what is how can you ever believe that extrapolation is gonna be right? There is absolutely no argument where you can say extrapolation is gonna be doing the right thing unless you have one piece of knowledge. You have the complete knowledge of the structure of the function you try to fit. Otherwise, extrapolation is gonna be horrific. It's always gonna do the wrong thing. I have no guarantee. So I personally, what we do in learning algorithms when we put them on robots, we have confidence intervals. And the moment we go far out, the confidence intervals blow up and we stop. We do not continue. Actually, we have another trick. We try to learn so fast in this area that we actually catch up with that. But if we have a very big confidence interval, stop. You fall. If you're a humanoid robot, you may just fall over, or you may punch yourself in the face, or God knows what you're going to do. Fine. And just the last component, we create basically new models simply to cover the entire input space, which just basically follows whatever input distribution you experience over time. Here's a little example how this works in a 3D example. So we just made up a little data set. It's come from some nonlinear function, which we also made up, create data points. This is what the function really looks like. It's meant to be interesting. What is interesting? Interesting means it has some flat areas, it has some very steep areas, it has some medium nonlinear areas. So it's a little bit annoying to simply go and fit it. And an algorithm like what I showed you will initially start with actually two big Gaussians and over-smooth the function, and then it takes about a second of computation, like 100 iterations, and it basically allocates more local models. The models shrink where there's kind of sharp edges, and they stay fairly wide where there's flat areas. And this is kind of the idea which we wanted to have. These things learn dramatically fast, really, really fast. And if you recall what I showed you the last time in adaptive control, this is actually inserting a system like this in a nonlinear adaptive controller, which is guaranteed stable in learning the right thing. And what you see is actually slowed down. It learns much faster. So the graphics slow it down. No, it doesn't have to be a Gaussian. You can use any, so basically, what is the knowledge about these kernels? You can show that if you use an asymmetric kernel, something which looks like this, there's always a symmetric kernel which is better. That has been proven. So thus you're just stuck with something which is a symmetric kernel. And then you can use any kind you want. So actually, statisticians have been using truncated polynomials, which basically hit zero directly, don't have these kind of smooth tails, and then basically you have to clip things. You have a discontinuity at this point. The Gaussians are just easy to do the math with. That's really the only advantage of them. But practically, you can use many other things. And there's a catalog of kernels which are good for different things. So here's a toy example on a robot, where the robot basically learns a model how this pole is working. Basically learns the differential equations of this pole, and from that it can compute a controller. And this is a robot which has literally no clue. It just wiggles initially around with its fingertip to see what this pole is doing. It's visually perceived with these kind of color vision systems. And it learns basically how to create the right controller, and it takes about 7 or 8 trials or something like that, and it can do it. This is actually not a very complicated example, but you can see how fast the systems can learn. They really incorporate data at high frequency and get things going. Slightly more complicated. This was actually a devil sticking robot. It's like 20 years ago that we did that. And it's the same idea. It basically learns the dynamics of how the stick bounces between the two hand sticks. And after it has the model of that, it can actually compute a controller and get better at this. So this is relatively complicated. You can try this yourself if you find a devil stick and see how long it takes you to learn it. Kids usually take half a day to get going on this. That took about, 10 minutes to get to this point. The most annoying part is me going there and putting the stick back on. And the good thing, it never stops afterward. Just works forever. And I showed you that video before, basically the same idea now, putting this on an even bigger robot, which is higher dimensional, and the controller is more complicated. Works the same way, yes.
So what is the dimensionality of the space where you're now searching?
This space was 10-dimensional mapping to 5 output dimensions in this example. And here comes one more depth dimension. That means 12 dimensions to 5 output dimensions as well. So it's very abstracted. It's a task level controller. So someone basically had to come up what are actually the controls at the stick level and how to do that. And then, yeah, go ahead.
And this is some low-dimensional manifold interspace, and you want to be in a certain region, and the stick is fine?
We just care about basically, we had only one goal. We wanted to hit the one stick such that it ends exactly in a mirror symmetric image on the other stick. That was all. Whether there's a manifold or whatever there is, I have no idea. So It's essentially it's just there's a set point task. We want to just have it go back and forth, and it looks symmetric from the one side to the other side. How it figures out how to do that, the algorithms about that, how the solution space looks like, I have no idea. All right, so this is essentially just a quick warm-up. Yes, oh, lots of questions. No barbecue at all, okay? Good point. You make them up. Let's be very simple. For many things, you can make them up simply. So pole balancing is a simple task. Since all what I want is I want to stay with my fingertip here and have that stick straight. So that's, again, a very simple cost function I can come up with. OK, I can do that. Try it with a pencil. Much more challenging. In more complicated scenario, the devil sticking was already, actually it was not so hard since we could simply say it should be on the one side like this and the other side like this, and you just make it up somehow. What is more complicated is how you define controls in task space. It's basically say, okay, I have a launch velocity, which is somehow a two-dimensional velocity. It's a vector in 2 dimensions. Then I may have a threshold from which I start that. It means the hand stick gets actually kind of compressed, and a certain level of compression you start hitting. And then you also have to determine a point where you want to catch the stick when it flies over. So that becomes actually this 5-dimensional command vector, which becomes more complicated. This is all made up based on intuition. This is not really what you want in the long run. At some point, you want to automate that. I'll show you a little bit towards the end things which are more automatic than this. Yes? That is before C2, actually. So we did some other work afterwards on online learning controllers. I'll show. So you're talking about kinematic singularities in a robot. So these days, kinematic singularities, we don't care about them anymore. Avoiding them, you can optimize them away. In the end, whenever you basically, so this is about, people don't know that most likely. Let me get rid of the stick. What is a good example? Let me see. I have to draw that, since my arms are unfortunately human. So, okay, so here is a robot for you, okay? Very pretty. Now let's focus on the arm. Let's assume the arm basically can swing up and down here like this, okay? And it can rotate like this, and then it has additionally an elbow. Okay, that's nice. So fine. So it's essentially an arm like this, if my left arm to do this properly. So this is my elbow, this is my shoulder, and then I can rotate like this. Cool. So with 3 degrees of freedom, I should hopefully be able to control a 3 degree of freedom external space, which is our Cartesian space, which most of the time will work. Let's see in this particular case. If I basically turn my arm like this, then I can go in this direction, means in the forward direction like this. This is okay. I can go up and down like this, which is okay. I cannot go inside, so that's a little bit of a problem if the arm is stretched. So I would have to actually get this elbow a little bit flexed. Okay, let me change that. I have to put it in this posture, then I can also go inside. But in this stretched posture, I essentially gave you what is called a singular posture, since there's one dimension in which I cannot move at all. That means in this direction, there's just no way I can move. Okay, so I cannot, when the arm is straight, in this direction, I have no degree of freedom which can create a movement. And that is called a singularity. When you basically put this into robot algebra, you basically get inverse, ill-conditioned matrices, which you can't invert anymore, and you create stupid solutions which make no sense. Practically, you can these days simply avoid these things by putting optimization criteria which keep you away from that. And then, and if you work with highly redundant system, it doesn't matter either. But we can talk about this more. This is a little bit more of a technical system. Reality is what you do these days. You go to Steve, and you use QP optimization on everything. And it gets rid of all those things. It basically just works around them. OK. What's good or bad about these locally weighted learning algorithms? And there's a couple of things which people don't like about them. The one is that they break down in high-dimensional spaces. The idea is essentially, I'll come back to this in a second, that in a high-dimensional space, you may need an exponential number of those guys to cover the space. But there's some other arguments as well. You will see this. If you have a high-dimensional system, let's take this humanoid again, and I have to potentially work in a 150-dimensional space, then I have to start inverting in linear regression or locally linear regression 150-dimensional covariance matrices. They are never full rank, ever. And you have to figure out ways how to work around that. People may say this is not really what we want to do these days. We want to do graphical models and Bayesian inference, and this is all much prettier. And there's some truth to that. And there's also gradient descent algorithms always have tuning parameters, which can be annoying to find out and make them robust. So let me just quickly look at these things. And I go a little bit faster to that. It's just giving you a glance of what you can do in order to take this basically nice, simple framework, which is literally trivial to implement in any computing language, half a page, and take it and make it a little bit more powerful and more robust. So the curse of dimensionality. So in high dimensional spaces is weird things which happen. If you take basically a sphere, or a circle, let's start with a circle, and I put data points in here, it's pretty easy to fill it with data points. And they're uniformly distributed, and so they are nicely everywhere. Now let's make this a 30-dimensional sphere. Guess where the data points hang out? They're all sitting on the surface, exactly. And they all start to be very far apart from each other. Really, really very far. Now, these kind of neighborhood methods, these kernel methods in general, lived from the idea that you somehow have in your kernel not just one data point, but multiple data points. Now, if all my neighbors are far away, then I have to stretch out really very, very far. So my kernels have become really big. If they become really, really big, they will also basically smooth over nonlinearities way too much. And then this becomes actually a very useless system to work with in high-dimensional spaces. If, of course, the data is truly high-dimensional. And this, you can create data sets which are like that, but in practicality, physical systems don't do that, which is really nice. And the intuition behind this, so fine, here's a two-dimensional space, here's a circle, so there's obviously a two-dimensional data set. But if I zoom in, just on a little circle inside of just looking at one part of this surface, then this is almost like a one-dimensional data set. And if you now take this example analogy and look at human data, so we did that. We took a sensuit, it's an exoskeleton to collect data of humans, collects 35 degrees of freedom. And this was Mike, and he was running around with that and collecting gigabytes of data. And then we basically did a local dimensionality analysis. This is essentially a mixture model which tries to fit local kind of reduced dimensional Gaussians to it. This is called Bayesian factor analysis. Zubin would tell you a lot about that if he had time. And looked at basically how thick are these distributions. We're not talking about manifolds, very important. These are distributions. There's absolutely no reasons why these distributions shouldn't be 105 dimensional in rank. But they turn out to be mostly about 6, 7, 8 dimensions. Some go up to 21, but the majority is actually very low dimensional. And it's not very surprising, actually. Humans move very, very regularly. And similar data actually has been replicated by Daniel Wolpert's group some 5 years ago in England. So the data which we're creating is, in the end, lives on thin distributions. And if we can kind of exploit these thin distributions, then we can actually use these local models or kernel models as well and work with them. And I'll just give you a quick glance how you can actually go about doing that. So let me now do graphical models. Go back to Chris Bishop's lecture. So this is linear regression as a graphical model. This is an output node. These are my input nodes. Gray shaded means this data is given. Boxes means it's something which is non-probabilistic, and circles means it's a probabilistic variable. And this is just what you saw before. Now, this time we derived it with maximum likelihood, and we basically assume a Gaussian distribution for the noise, and we get the regular regression equations out of that again. So nothing special. let's do the next step, make it a little bit more interesting. And this is kind of a very interestingly weird thing to do. So before we had from x to y just a single arrow. And now we just created some additional variables here, and we call them z's. They are just kind of made up hidden variables on the way to the y's. So I just made my problem more complicated to some extent. So why does that make sense? So here's the idea. From x to z, there is actually a regression coefficient which maps x to beta times x. This is essentially what is shown here. And then we have some noise which gets added in this z node. And then all the z nodes are simply added up to y. This turns out to be still linear regression. The interesting thing about this kind of linear regression is now there's no matrix inversion in it at all anymore. It becomes an EM algorithm, so you cannot fit it one shot. That was the beauty about linear regression. But now this is an EM algorithm which is accurate and will basically come to the least square solution, has to iterate, but no matrix inversion. So why would that be useful? Well, we'll see in a second. We can do a little bit more. Now I add more circles. Circles are good. And what we do now, we basically put a distribution on the regression parameters. So we actually now basically go one level up in the Bayesian hierarchy and make also the regression parameters probabilistic. And this becomes essentially now a way to regularize the regression vector. I can regularize it to be as short as possible, or I can, in this particular case, I start regularizing each coefficient to be as minimal as possible, which essentially creates a sparse vector. So this becomes actually a sparse linear regression model, which again, I can fit with an EM algorithm. I have to do a little bit more work. It's in the framework of automatic relevance detection. Chris talked about this most likely. Yes, no, maybe. Doesn't talk about this. It's essentially complexity regularization in these models so that you fit the kind of simplest model possible to the data. And this is now actually becomes very useful, since what it essentially does now is a linear regression model. Nothing has changed, but it will kind of push every regression coefficient down to 0 unless it has really evidence to contribute to my regression. And it can be just analytically, you write the equations. In the end, it's an analytical algorithm. You iterate it with EM, and it basically comes up with the right solution. And this is now becoming a very robust regression technique, which I can put in these kind of locally linear regression models. Since now the matrix inversion doesn't bother me anymore, since I don't invert a matrix. I regularize the regression vector. Essentially, it means I figure out how thick is the distribution in which I'm actually working and make it as minimal as possible and can start fitting things again. The only disadvantage I have to iterate with EM algorithms, which you can still do fairly fast since the update equations are not very complicated. And if you want to make it even more complicated, I'm not going to explain that. This is now truly a fully Bayesian kernel regression or linear regression model. This is what I created the little box for. There was a PhD thesis of Joanne Ting in my lab some time ago. It still has the same ingredients. Basically, here are the x's, there are the z's, they're mapped to the y's. Here are the weights from the weighted regression. They have some hyperparameters. They have to be regularized. And in the end, the entire model, it's not something you can solve analytically anymore. You have to do a variational approach. That is essentially what Zubin told you a little bit about, at least. But you get analytical update equation. And this is essentially the variational approaches are very interesting for us in robotics, since we prefer analytical update equations, which are approximate more than sampling methods, which may be more accurate, but we can't compute them at all on the real robot in real time. So let me show you for a second what these things can do, which is more entertaining. So I showed you initially this cross function, and now I see what I did. I took the data sets which I had initially and just rotated it arbitrarily in a 20-dimensional space. So it's a basically two-dimensional, it's a two-dimensional surface somewhere in a 20-dimensional space. You fit it now with these dimensionality reduction local linear regression methods, and you basically recover this after you return it back in a three-dimensional space. So yes. Yes?
So is there any reason in particular that you have to be Bayesian in this context of robot learning?
The Bayesian component usually helps us to not overfit, to regularize the parameters. Remember, I have this issue when my kernels shrink to thin and just focus on one data point, I go into massive overfitting. This entire world of kernel regression, locally weighted regression methods quickly start fitting a little bit too much noise. And the Bayesian methodology allows me to regularize against that. And thus in a very pretty online algorithm without using leave one out cross-validation methods or things like that. Does that answer the question? The answer is nothing. Okay, it's good.
Yes, thank you.
And just showing you, these are kind of learning graphs if you basically learn in a 2-dimensional space in blue, in a 10-dimensional space, in a 20-dimensional space. I'm always using this simple cross function. And you can actually see in terms of data efficiency, all these methods are not so different. And they're basically, in the 20-dimensional space, takes a little bit longer to get there, but I get to the same point. I need a little bit more data until I figure it out, but it's not too terrible. And the number of local models you allocate over time basically is pretty similar, which is not surprising since the local models are just allocated basically in this kind of, in this case, 3-dimensional world and not further than that. Some time ago, we basically put this actually on this 30-dimensional robot, and it's just trying to swing its tennis racket and learn an inverse dynamics model. And this is now turned on literally within a second. It learns gravity compensation, and it starts learning the Coriolis terms and the other terms in the inertia matrix, and gets better and better. And this works in real time. And then now just learning is turned off. You can see what it looks like then you turn learning back on, and it keeps on going. Here's a similar example where the robot actually learns how to track this ball with its fingertip. And it's learning now an inverse kinematics model, which in this case is a 60-dimensional space to learn in. And you just saw how long it took to get to the ball and basically track it. It took 2 seconds, and it has the model. So what is pretty about this? This kind of learning has the philosophy that we have never the opportunity to get representative data sets for what we want to do. Instead, can we create learning algorithms which can learn so fast on the fly while we are experiencing new data that I don't care about which distributions are out there. I just learn where I am very, very rapidly. Yes?
How close do you initialize? How do you initialize the kernels?
Those, in this particular example, it was all initialized to 0. Yeah, linear regression learns so fast. It just learns so fast. It just needs, in the end, if you get, in this case, at 500 hertz data points, in no time, in a fraction of a second, we have enough data to fit a confident enough model. And then we just improve based on that. And this is another fun example. So initially, in this robot, we couldn't do pole balancing because the entire body was moving too much. So we needed actually to learn the entire inverse dynamics model of this robot to learn about the coupling between arm and body. It's kind of annoying, you move your arm and you don't anticipate the coupling between the arm and the body, and then your body starts shaking and the entire thing starts shaking and loses the pole. All right, now I need to make progress. So this was a little bit more about model-based robot learning. It's a different set of techniques than what you partially see in machine learning. We have different problems. We care a lot about doing things fast. Sometimes speed, better high updating speed, and less accuracy. Still, ideally, we would like to get this better at these things. People have been trying to do similar work now with Gaussian processes in particular, which is fabulous. Gaussian processes are a wonderful and very powerful machine, and Philip Henning will tell you a lot about them. The problem is getting a lot of data and updating Gaussian processes in real time when you have growing data sets becomes more tricky. And I'm not sure whether he talks about it or Matthias Seeger is going to talk about it. Yes, Philip is going to talk about it. Okay, so we'll see. Now, let me now make one step further. So I've been very model-based, and I will want to go over to reinforcement learning now. And we had this question in the last lecture that how about where do all these desires come from? And I will essentially start addressing that right now. And what I'm going to do right now, I want to address systems which have somehow some planning system here, which then gets put into a controller and executed on the robot, and you get coupling back. And I will come back to this. Let me just get going a little bit on reinforcement learning, and you will see how this fits together. All right, reinforcement learning. That's literally what it is about. You try something, someone tells you, or yay, and that's it. So you don't really get target information what to do, you just get a reward. And you try to learn based on this reward. And all of you were raised that way. Initially, someone shows you how to do something, and then you try it yourself. And you say, oh, grasping is cool. Oh, let's grasp the hot stove and see how that feels. And then you learn something amazingly fast, actually. Usually one data point does the job. And you get better. And this is somehow, this trial and error learning is something we all have to do, since there's a lot of, in particular in motor control, nobody ever will tell you, oh, you did not flex your biceps enough. That information is not there. It's like, oh, you missed the ball. And so we need to basically figure out how to learn from things like that. So, problem, how can a motor system learn a novel motor skill, primarily based on rewards? And reinforcement learning is kind of the most general learning control approach which we know. It's very closely related to optimal control. You will see that in a few slides. It has just one problem. It has been having problem to scale to high dimensional things. So most of reinforcement learning was done in computer science with grid worlds, discrete state system, discrete action systems. The moment you go into high-dimensional things, these kind of discrete worlds basically get an exponential explosion of the number of states and actions you can take, and then you can't learn in them anymore. The approach which I will try to show you in the end is that we will initialize a system with imitation learning and then provide an objective function and then basically do trial and error learning to get better and try to make this manageable in full humanoid systems, for instance. So the first thing I want to do is I want to tell you a little bit about reinforcement learning, since I'm not sure how many people have seen that. So here is some intro slides on that. Reinforcement learning, terminology. So in general, you have a robot system, and you have a policy. That you've seen now a couple of times. Now they are written as probability distributions in case they happen to be stochastic, which is not so unlikely in some scenarios. But you could also just write analytical functions in there. The policy creates an action, it gives it to the robot and the environment, out comes a next state and a reward, which tells you how well you've been doing. You try to either minimize or maximize, in general, optimize the reward, and hope you get better over time. Reward functions. The reward function is simple. This is the thing which tells you how good you are. It tells you what's immediately good or bad. Standard example for all of those who like to smoke. Okay, you go smoke, you get an immediate reward, you're happy. That's cool. But then comes something different. Then comes the value function. And that is your long-term reward. And that's the thing where you get lung cancer, you die a horrible death, and you're miserable, you make everybody miserable, so no good. Did that work? Fine, but this is the real difference, okay? Reward functions is about immediate rewards, value functions about long-term reward. What's immediately good may not be good for you in the long future. And the long future is really what matters. And the last thing is models. Now we talked a lot about models. Models simply help you to predict the environment. If you're in a state and take a particular action, where you're gonna be as your next state. That's what these functions are about. Okay. You can make this simpler. Policies are what to do. Reward is what is good. Value is what is good because it predicts long-term reward, and models what follows what. I go very quickly through reinforcement learning 101. It's just as you've seen a little bit what's in there. It's actually not very complicated at all. So the value function is actually one of the key components. If you can compute the value function, you know what to do. Since if you have the value function is just a complicated function over your state space, you're sitting there somewhere in the middle of that landscape, like somewhere Rocky Mountains or whatever, and then you basically ask, so what is the right action to take next? And all what you do is you look around, okay, where is the next highest or lowest value, depending on what you want to optimize or not, and that is the right action to take to go in this direction. You will see this more formally in a second. So what is the value function? The value function has a very simple definition. So for a particular state in which you are, which is just x right now, you simply start summing up all the rewards over time until either infinity or you have a certain terminal point where you don't want to continue anymore. And you may want to discount that with some discount factor which is between 0 and 1. If it's 1, nothing happens. If it's 0.9, basically things which are further in the future don't matter that much anymore. So this is very simple. And you just take an expectation operator, since it's maybe stochastic after all. Then there's something else that the reinforcement learning people need, and this is called the action value function. It's almost the same thing as this thing, except for one. You are in a particular state and take a particular action, and my monitor just disappeared. That is not what it's supposed to do. Interesting. Okay, fine. We'll fix that and continue. Good, here we are. So you're in a state, you take a particular action, and then you basically compute the value if you take this action and from then onwards go optimally ever after. So it's essentially you start with this and then you basically accumulate your rewards. The only difference is that you take a particular action initially. You do not take the optimal action, you take a particular action. And this is what is called an action value function. You will see in a second why this matters. Right now it's just a definition. Bellman's equation. The basic idea behind Bellman's equation of optimality is that if you sum up your rewards over time like this, you can basically always pull out one of those discount factors and then write the sum there. So I'm just transforming these series again and again, and you can essentially write the current reward as the immediate reward plus discounted times the complete future summed up reward. Okay? So this is just essentially what it's saying is you can always look at what's my reward by looking at the immediate reward, and then at looking at the next state where you are, what's the value of this state? And that these two things added together become your total value. And then we can actually go to Bellman's principle of optimality. So the value of a state and an optimal policy must equal the expected return for the best action from that state. The expected return is the current reward, which I'm getting, plus the expected, that means the value function, of the next state where I end up. That must be obeyed for optimality. And that creates actually a very interesting consistency equation. That means for every state in which you are, if the value function is correct, I basically get a reward in my state, look ahead, what's the next optimal state? Is this the state which has the highest or the lowest value function? And then if it's optimal, my current reward plus this value must actually be the value at the current state where I am. Okay, the value at state X has to be the reward which I'm getting here plus the value of the optimal state which follows. And this consistency equation is all what matters in reinforcement learning, since if we can enforce this consistency, then we find the optimal solution. Now, actually I need to go back one, oops, wrong direction. Go back one more time. What is interesting here is one component. In order to compute the best action in a particular state, you actually need to know if you take an action where you will end up. So you need, if you take u in state x, what is xt plus 1? So you need to have a model of the world which tells you where this action is going to take you. That actually makes these kind of approaches which use the value function directly model-based. You need to have some form of a model. And the interesting part about this state action value function is you don't. So if you do the optimal Q function or state action value function, it looks actually like this, that you need the current reward and then the optimal value evaluated at the next state. It means where you look at all the actions at the next state. So what does that mean? It essentially means you are currently in a state X. You take an action U, which is given. So that's why this is called the action value function. You take an action U, and you end up at another state. And then you look at what is the best action there. And basically, that gets into this kind of consistency equation. If you want to evaluate, after you have this Q function, let's make this slightly different. If you want to evaluate with a Q function, what is the optimal action? You just add a particular X. You go through all the U's you have and look which one has the highest Q, and you're done. You do not have to predict the future. And that was actually in the end of the 80s, beginning of the 90s, a big difference to do reinforcement learning. Okay, all what I wanted to basically convey right now really quickly is the idea of value functions. These value functions were the central theme in reinforcement learning in the 80s and the 90s. And let me show you how value functions look like. So some simple examples. So here is a super trivial dynamic system. It's actually a little stick which is hanging here from a hinge, and it has a motor here, and you can swing it, and you can swing it up. That's what your task is. So it's actually very trivial. It's a one-dimensional control system, and it's a second-order system, so it has a position and velocity as state space. So there's a two-dimensional state space, so I can plot them. Very nice. Position velocity is the state space position velocity. I can show you the value function. I can show you the policy. So this is what the optimal policy and the corresponding optimal value function looks like in this case. Aha, is what you think. Cool, colorful, most interesting. Now, it is interesting, but you have to look a little bit more closely. So here's weird stuff. Look at that ridge. It's nasty. Okay, here's a little ridge as well. This is here, the value function. Look at this ridge. Here's smoother, but here's essentially a discontinuity. There's discontinuities there. So these functions, which are pretty functions, they're very nonlinear, and they very quickly have discontinuities about what's good and bad. And you can actually think about this yourself. Now, if you play chess, you can create these value functions for chess as well. You know, and then any position in the board, let's take one where it's almost at the end of the game. If you move in one direction, then you win. If you move in the other direction, you lose. So it's a discontinuity. It's a sharp bridge between success and failure. And that happens in these functions all the time. Now, the moment you now take, so this was an example where we still can enumerate or basically discretize state and action very nicely. It's not a big deal. If you take this in high-dimensional spaces, we can't do this anymore. And if you take in high-dimensional spaces, then I have to actually start approximating these functions with function approximators. And there's hardly any function approximator which will get these ridges right, since that requires an incredible amount of knowledge to fit those discontinuities. Most of them will smooth over them very, very lovely. And when they smooth over them, you will make the wrong decision up there when you get to this. Additionally, what's a problem is basically in high-dimensional spaces, you saw these max operators. They were very easy in equations before because these were discrete equations. So I could enumerate all the U's and figure out which one is the right thing to take. If you do this in a continuous action space, you have to just do a line search, or if it's a multi-dimensional control signal, you have to search a landscape, what's the minimum, which may take a long time. You may not even find it. So this is essentially what makes these kind of approaches really hard and complicated robots. So I can only show you simple examples with not so high dimensional systems. So this is some work Kenji Doya did. He's in Japan some time ago, where they tried to learn with reinforcement learning how this little guy can stand up. And after some miserable 400, 500 trials, it actually figures it out and can do it. Very pretty. But it's a very low dimensional example. It's mimicking a humanoid, but in the end, it has only 1, 2 motors. So it's not a very high dimensional system. This is some work Chris Atkinson did some years ago, actually first demonstrating. This is like seeding a policy from demonstration for a robot to swing up that pendulum as well. And he used some very cool, very efficient algorithms to compute the value function and then figure out the controls for that. And the robot could actually learn that in 5 trials. And now he demonstrated something which was swinging back and forth twice before swinging up. And then the robot finds the closest solution to that as well. All right, let me move ahead before I run out of time. So this is what I tried to mention before. So this was kind of reinforcement learning from in the 1990s and in the 80s, which doesn't really scale to complicated robot systems. And what I would like to show you for a second is this new wave of reinforcement learning, which does work on big robots, and that's essentially trajectory-based reinforcement learning. And the idea is here, instead of trying to learn over state space, I learn along trajectories and try to basically improve around the trajectory until I find a local optimum. The problem, I can only find local optima. I cannot find the global optimum. These methods were able to go and find a global optimum under the assumption that you can literally explore the entire world at least once. Yes, 15 minutes. I'm doing fine. 50 minutes? Excellent. All right, so let me show you in a nutshell what we're going to do in order to get to reinforcement learning of that kind. So I'm back to this control diagram. I've now shown that a couple of times. And what I'm going to do now is in this box, I can put in a generic control policy. Actually, then I would subsume those two orange boxes in this there as well, where I learn a motor command, or I could just learn a plan, a kinematic plan. It makes no difference for the algorithms, to be honest. Whatever, how you code the problem, what you want to represent, what you call a control command, whether it's the change of state, a desired state, or whether it's a force or torque to a motor, doesn't really matter. What we've been using in the past, I'll show you that in a second, we've been using planning systems like that. So we were planning actually desired trajectories with reinforcement learning and then basically giving them to a controller so we don't have to learn the control commands and stuff. And these desired trajectories look like this. And this is just a second order, it's a spring system again. You saw the spring system the last time in one of my slides. So this damped spring system is the first part. Back here is a good friend, is a function approximator. And this function approximator will allow me to modify this kind of simple damped spring system to become an arbitrarily nonlinear damped spring system. And most important is here again, this is some basis functions with some parameters. W comes from some Gaussian basis functions. B are some parameters. X is a little special timing variable, which I'm not going to explain right now. It just basically helps me to basically make progress through time. Just what you can do with systems like that, essentially, this is a student of mine, Peter Pastor. He's basically teaching a robot some simple reach and grasp movements. And what is interesting about putting this into differential equations is there's something which is G, which is a goal state, and that you can change as you wish. And automatically, the robot will basically change its movement to the next goal if you change the goal. So now the goal is here. It moves. Oops, no, it was not here. It was out there. OK. So it's essentially a system which has a certain level of generalization. That's what makes it appealing. And it also, because differential equation, you can prove stability, and it's stable and does the right thing. Again, you can see the same movement primitive, the same parameterization. You don't have to relearn in order to get to this point. You just have to set the goal state appropriately. And I'll just, another video where it actually does something similar, which now pours with a bottle of water, becomes a bartender. So this is essentially what is taught here. OK, you get the picture. It's just a representation which can basically capture a desired movement, and we have a function approximator in there which can improve over time. So let me go into this idea of trajectory-based reinforcement learning. We do something very similar as before. We define a cost function. We sum up the rewards. But now we sum them up over time. Okay, time matters. We are now in a time-based representation. We are not in a state space representation anymore. And you say after time, capital T, I'm done. Then I have this kind of parameterized motor primitive or policy, which has a parameter B. It may have a goal parameter and has a state dependency. And then I can figure out now, how can I optimize this cost function? Again, I want to optimize it. It means minimize or maximize it. And this I do by changing those parameters B. And this is just a matter of gradient descent. So depending now how you basically have this policy coded, in our case, it has linear parameterization in the function approximator, which makes life very easy to take derivatives. And then you can basically run the entire calculus through and basically get the update for these gradients. And there's a lot of knowledge about that, which I'm going to skip right now. But you get some ideas of that. So here's basically, again, a simple 7-degree of freedom robot, which tries to hit a baseball. It's a toy baseball. It's not a really heavy one. And basically got a demonstration from a human, from me before. I'm really bad at baseball, but I tried my best. And then it takes about 150 to 200 trials to get better at this, until it finally hits the ball, and it basically hits your colleague working on a computer in the other room. OK, so
what was the reward in that case?
In this reward, the reward was to basically that the ball, which is actually colored, which a color vision system can see, that it flies as far as possible. And it works in the end. It's kind of fun. Yes? Don't ask questions.
So the reward, so does the reward depend also on the length of the trajectory?
No. Only
Because you sum up the reward, right?
in this case, there is a small penalty for using too high motor commands. So that's a simple regularization that the thing doesn't go wild. Otherwise, which people do all the time, since we have only certain limits of what we can basically put in the robot as motor command. But the main criterion was how far this ball can fly. So let me quickly go ahead before I run out of time. So this was gradient-based methods. They actually were started about 20 years ago. And they were nice, but they converged very slowly. What you saw actually right now was some work of Jan Peter's thesis where he used what is called a natural gradient, which is a special gradient which is much more efficient in its convergence. So a little bit about most likely what Steve has been talking about today as well. So let me show you a touch of history of reinforcement learning with trajectories. So this is actually the reward function and this kind of parameterized policy, which I showed you before. What you just saw was something where we updated with a gradient descent method, which was actually the natural gradient. There's other methods you can use. There's actually a probabilistic method, which is kind of reward-weighted averaging. It's also something Jan Peters has been working on, also Peter Dayan some long time ago with Jeff Hinton. I'm not going to tell you too much about this, since it's actually very similar to what I'm going to show you in the end. There is a version where you represent Q functions, which I showed you just for a tiny second, along trajectories. You basically represent the value function along trajectories and basically learn on that. And then there's recently, we've been working on something which is called path integral reinforcement learning. And I just want to show you for a tiny second how this looks like, because it has this nice flavor of combining optimal control with, in the end, probabilistic learning, which is very pleasant as a derivation. So let's go to it. The good thing is now you know everything. This is so cool. I can talk about control affine systems, and he says, yes, of course. So here's a good control affine system. So here's my good friend. X dot equals f of x plus g of x plus u. And now there is some epsilon, some noise term. So I make it a stochastic differential equation just to give the system in the end some ability to explore it. Since these systems, all the motor systems, they have to try new things in order to improve. If they do the same thing, they cannot improve. Okay, then we have a cost function. The cost function has an arbitrary function which depends on the state, and a quadratic functions for the motor commands. You will see in a second why I need to have a quadratic function in the motor commands, otherwise my algebra doesn't work anymore. And my the long-term cost I want to basically optimize is the expectation over essentially integrating over this cost function. And potentially I have a terminal reward. This is what this Q of t stands for. That means if you win, then you get $1,000. Or if you don't get anything. So again, I want to optimize, find the motor commands which minimize or maximize or in general optimize. In this case, it will be minimization, these costs. And this is actually, I've promised you model-free reinforcement learning. Right now, this is model-based, but you will see why it becomes model-free at a moment. So, how do you do the derivations? I go through this really quickly. It's just to give you a sketch. You can look this back up in the slides if you get the slides at some point. But the derivation is actually not very complicated. So you start with something which is called the stochastic Hamilton-Jacobi-Bellman equations. So what is that? I showed you before the Bellman equation. The Bellman equation was nothing but the discrete version of that. Now we're in continuous space and action spaces in continuous time. So we need actually what is called the Hamilton-Jacobi-Bellman equation. That's the only difference. If you look at this, this is actually very similar than the Bellman equation. That first it has the immediate reward, and then he has something which basically involves the function which we have a model of. And now in this case, it has the partial derivative of the value function in there that's coming from the continuous time derivation. And then it has another term which is comes from the stochastic component of these equations. Now this is a textbook equation. You can just get a optimal control textbook and we'll find this equation in there. So it's nothing which we made up. It's been around for a long, long time. Okay, so this is the equation we have. Now we basically have to do this minimization with respect to the motor command u. And you can do this, you basically plug everything in which you know. You plug in the reward function, which we know, which is kind of q of t plus u transpose ru, everything you know, and then you differentiate with respect to u. And now you see why I can only tolerate u in a quadratic function. Since if I differentiate with respect to u, then I just have one u left, and I can solve for u, and in the end, I basically get this optimal control. If this here would be a nonlinear function, I could not solve. I couldn't do that. But my q, this state-based reward, can be anything. So fine, I get the optimal controls here. Yes, a little bit more. People were asking too many questions. So the story then continues. You have these equations, you have this knowledge, you have the knowledge of the system dynamics. Again, you start plugging things in. There's only one step on every slide which happens. And you get that big partial differential equation which is ugly. Why is it ugly? Not because of the parentheses. They're just there. There is something here which is annoying. There is a derivative of the value function, partial derivative of the value function with respect to x. And here it is again. That makes it a quadratic function in V. And that makes it nonlinear. And nobody knows how to solve that thing in general. So that's annoying. And then comes a very cool trick, which Bert Kappen from the Netherlands had some time ago. Actually, this was published in a book before, again, even longer time. He looked at this equation and basically said, if I replace the following things here, this is sigma is the noise variance of my stochastic term, R is my matrix which I had in the command reward. U transpose RU was the cost of my commands. If they obey this relationship, this is an arbitrary lambda, and I take the log transformation, basically I define V is the log of some new value function psi, then I can transform these equations and they become suddenly something which is a second order but linear partial differential equation. Looks all a little cryptic. Turns out to be the Chapman-Kolmogorov partial differential equation, in case you haven't seen that. It's an equation which has been well studied by physicists, and they know what to do with it. And the beauty is, they know how to solve it with an approximation technique. And this is actually going back to Richard Feynman's work, and it's based on the Feynman-Kac theorem, which says to solve this partial differential equation in order to get this value function psi, you just have to evaluate something which is called a path integral, which is essentially that expectation operator in the end. And the way you do is essentially you try out multiple realizations with different noise and basically can from that figure out the value function. Okay, very fast, I know. And from this knowledge, finally, you can compute the truly optimal control, which include everything. So actually, you don't have to represent the value function. You can just go directly to the optimal controls. It's a slightly convoluted derivation, I know that. But it's actually very pretty, since it takes an optimal control problem suddenly into something which is more like a probabilistic problem where you have to figure out an expectation operator. And the expectation operator you can figure out through sampling. And this way, you can actually suddenly create algorithms which are new reinforcement learning algorithms. So in our world, was essentially our parameterized policy has actually this control affine structure, except that we have parameters and not motor commands. But that doesn't matter what you want to call these guys, thetas or u's or parameters or motor commands, who cares? If you want to optimize those parameters, we can do this as well. And you can basically now pull this through and create algorithms which do that, and all this kind of complicated optimal control stuff boils down to simple algorithms like that. This is essentially saying you try out multiple trials with different noise profiles. At every moment of time, you use a certain motor command or a certain parameter vector, and then you just average these parameter vectors together with something which is like a reward-weighted averaging. Let me show you in a much nicer slide how this looks like. And this is a more intuitive way of explaining that. Let me go fast, and then we're almost done. So here's the idea. Now, forget about all this math. Here's a point which goes over time to the goal 1. It starts at 0, goes to 1. These are position profiles. These are velocity profiles with different levels of noise added every time. So every realization has a different noise level. Okay. At a particular point in time here, All what I'm going to do is I'm going to sum up the reward along the remaining trajectory. Okay, this is essentially summing up q of x and the basically command squared with some factor and just summing it up. The integral becomes evaluated in discrete time simply a sum. All right, then I take that reward and run it through an exponential function with a negative sign in there. That makes it actually a weight between 0 and 1. And all what I'm going to do for all these different trajectories, I'm averaging together with a weight the motor commands that were used at this point, a reward-weighted averaging. And that's going to be my new and more optimal motor command. And I can iterate that to get better and better. And that's all what's behind it. It's really cool that actually from this relatively complicated approach, what you get out is some incredibly simple algorithm. Okay. And let me remark one more component. Now, if you apply these things now to a complete control system, again, you know these equations. You've seen the rigid body dynamics equations. You have seen a feed forward with PD controller. And now I just showed you that little motor primitive of parameterized policy, which I'm going to learn with reinforcement learning. You can actually prove that when you try to optimize a complete system like this with respect to those parameters theta, that's all that I need in order to create the optimal trajectory. You can ignore this equation and this equation entirely. They don't appear anywhere in the algorithms. That means essentially, with this algorithm, you can suddenly go completely model-free. You only have to worry about this equation, which has your parameter and nothing else but that. All right, let me show you some evaluations, and then I'm done. I'm not so bad. It's 5:26. I still have 3 minutes and 24 seconds. Okay, so simple examples that this works. So this is just a toy example to graph it. So this is a robot arm with 2 joints like my arm. It starts in a stretched way. It tries to reach to a target up there. But then I tell it, reach through this via point, so this intermediate point. Learn how to reach through there. This is it's just something made up. You can think of it as a very, very simple form of playing tennis, where you not just swing the racket, you have to also hit the ball. And basically, the system learns that over time, creates a particular trajectory. This is this red trajectory. These are other reinforcement learning algorithms in comparison. And what is nice, essentially, the system learns really an order of magnitude faster than anything which we've seen before, and very, very reliable. No parameter tuning. This one, in this algorithm, you only have to set the amount of noise you want to use for exploration. Everything else happens by itself. But you need the cost function, but that's a different topic. And this example is nice since now it's a 2-joint arm. I can make it, chop it a little bit more up and becomes a 10-joint arm. Now it looks a little bit more like a snake. You can do the same example and see how quickly it learns. And now it's a much higher dimensional system, but it still basically converges in about 600-700 trials to some decent performance and can make it 50-dimensional. Now it needs about 1,500 to 2,000 trials to get to perfect performance, but it works. It works really nice. So here's a more fun example. This is now applying this to this simulated robot dog, which has to jump over this gap. Let me see. This is some initial trajectory which we put in. You need to give it something to start with. You cannot start from nothing. And then within about 10 trials, 10 to maximal 50 trials, basically the performance improves very significantly, and it gets over that. And this is now actually optimizing 600 parameters very reliably, very nicely. Here's another example. Actually, this is the PR2 robot at Willow Garage. Two of my students, Peter Pastor, Mrinal Krishan, and together with Sachin Chita at Willow Garage have been working on that, trying to make the PR2 robot play better billiard. It's a very weak robot, so it cannot really hit the billiard ball very strongly, and so they basically tried to improve that with this kind of reinforcement learning algorithm. And you will see in a second what comes out of that. So basically, they had to put a camera up here. They basically told the robot to hit this point there and hit it as strong as it could. So this was what the initial policy could accomplish. And you will see in a second what basically after like 100 learning trials, the system could accomplish, and that very reliably. So these things are actually very exciting. You maybe don't know. So about 20 years ago, 15 years ago, reinforcement learning on average took about 100,000 trials to converge to do anything. And now we are suddenly in something which is 100, 200 trials, which is actually very similar to human-like performance. I have only videos to show, so you should not interrupt me. Okay, so this is a similar thing now, basically creating up a little task where the robot has to learn how to turn over a cube. Think of it as a big piece of tofu in a Japanese restaurant, and you want to just turn it over, see whether it's burnt underneath. And again, it learns this very nicely after a while. Let me show you one other example of basically where many of our learning algorithms came together, and this was kind of a learning locomotion problem. This is a little dog which is like this, and it had to learn to walk over rough terrain. And that actually uses this reinforcement learning inside to optimize the leg trajectories. It uses model-based learning in order to control better. It uses actually some support vector machine-like systems in order to classify which foothold to take. That is actually shown in a second in more detail. And basically, it was tested on terrains which it had never seen before, and it just had to learn to get over this. And it was actually a very good mixture of good control and a whole bunch of really useful learning algorithms which could accomplish this task. So this was kind of this foothold learning. Initially, the robot basically makes lots of mistakes, falls over all the time. And then basically, when it did a mistake, it was shown which foothold to take, and then it knew which foothold to take, but it also knew all the other footholds around it are inferior. And you can actually create a very nice support vector machine classification problem based on that, how to get better. Okay, it didn't come up with that. There was just no way it could get up these stairs unless you used the nose. And you need the nose here again. So the nose is a very suitable fifth leg, to be quite honest. Okay, 2 slides and I'm totally done. So I'm done, essentially, and you might want to ask what comes next to find we can do a little bit more movies. And so this is what's currently happening in the States, though. There is a big push towards big disaster robots. Let's see whether this works. Does it work? Have I done anything wrong? My movies usually work. Okay, there we go. No. How is that possible? My movies always work. Okay, no movies. That sucks. I'll pull up the movie. I can do that. At least the one is worthwhile watching. Yeah, you can. Movies.
We're a bit over time, but I think you can take a few questions. I think that's fine. So, any questions?
Any questions while I'm not watching?
Yeah.
Okay, we're getting there. Now I gotta get this mouse pointer to the right point. Oh God. So this is what DARPA currently wants to have as a disaster robot. And it started actually, this is a 150 kilogram robot. You will see actually the specifications as it moves along. It is about 2 meters tall, maybe a little taller even than that. It has an incredible amount of hydraulic power on board, so it can kill you multiple times in a section here. And it's meant to basically go out and help people in disaster scenarios. And you basically see different versions of how this prototype was put into being. And the big challenge is going to be how to make systems like this autonomous. So this is all very good control engineering. These are the same people who created this dog-like robot. And there's now 6 different teams in the United States which have one of those robots, actually 7 teams. And they try to make it work or destroy it. It's just $2.1 million per robot. It has a little bit of an Iron Man look, actually, coming back to this topic. So in the basically state space approaches, these problems really exist. When you saw actually this one example where Chris Atkinson was using the swing up, he had a hell of a time to actually get this to work and get a function approximator to really go over those ridges and represent them appropriately. In trajectory-based reinforcement learning, the way we've been doing it, there's no derivatives and there's no dependence on this kind of knowledge at all. So it doesn't show up so far in our world. This is really very pretty. Many of the approaches in reinforcement learning may work nicely if I say, oh, I want to reach from A to B. It's kind of, I'm doing something in the air. The moment you start touching something, you always get discontinuities in the world, potentially in your reward function. You hit something, you want to say, okay, when you hit this with the elbow, you get a reward of 1,000. That means a negative reward of 1,000 or whatsoever. And these discontinuities break most of the optimal control approaches, which usually require derivatives or second derivatives even in order to optimize. This approach doesn't bother about this at all. We've never seen any problems with issues when there's discontinuities in the world. And we have not discovered that the value function or the policies suffer from that at all. But that just means we haven't discovered it yet. Doesn't mean it doesn't exist. So just because we haven't made the experience doesn't mean that we are safe.
Are there any questions? Oh, there's another one here.
So you also use techniques like transfer functions to transfer the knowledge. So for example, this jumping dog, can you use the knowledge if it wants to do high jumping, for example?
Okay, so there's certain levels of transfer we can address, certain levels we can't. So why we use these kind of differential equations to represent policies was actually because they can generalize to some extent. They have an attractor as their goal, and no matter where you start, they will get you there. So that means actually they transfer the same task over a wide workspace, but they will not come up or transfer to something totally novel. And kind of the extreme examples over is if maybe of you who remember high jumping. High jumping, when people dive over that big bar, there used to be an alternative technique a long time ago, which was called the straddle. And people were literally diving over it. And these days, they go there and then turn around and go backward over it. Now, this kind of transfer from this one to the other technique is totally impossible for us to figure out. Transfer learning otherwise can be addressed to some extent, and some people have done this, but I basically learning parameter spaces of our motor primitives and basically generalizing to new tasks. But it's very immature work, I would say. So I don't really know what to do about it.